I'm F1, Mr. Bruns here again. Hopefully you were able to watch that previous video on an introduction into graphing systems of inequalities. We're going to look at two more examples here. This first example here has two different inequalities. One of them is going to graph into a line. The other one right here is not a line. This is going to graph into an exponential curve. So we'll start with this one right here where we have something written in y equals mx plus b form, where I have a slope, a y-intercept. So in this case, we have a y-intercept of 5, and then a slope of 1/2. So rise 1 over 2, rise 1 over 2, rise 1 over 2. Because this is not less than or equal to, it's just strictly less than, we don't use a solid line on this. We use a dashed line to represent the boundary. Dashed line, the boundary there. And once again, we're going to pick 2 points to determine which side do we shade on. Remember, we're shading all the points that make this inequality a true statement. So the first one is at point 0, 0. That's always an easy point to test. Right here, 0, 0 is clearly on the bottom side of that, that line. And then maybe we try the point -5, 8. -5, 8 looks like it's pretty clearly up there somewhere, and that's going to be on the top side of that one. So we try 0, 0, and let's see, we get 0 is less than 0 plus 5 is 0 less than 5. Yep, that's true. All right, let's try -5, 8. So 8 is less than 1/2 times -5 plus 5. So that's 8 is less than -2.5 plus 5 is 8 less than 2.5. No, that's false. So we are not going to shade on the side with -5, 8. We're going to shade on the side that has a 0, 0. So that's going to be all of this. Again, everything in the green region, if I pick any point in that green region and I plug that into this inequality, I'm going to get a true statement. Anything up here will not give me a true statement. That's what we're showing. That's what we're representing on this graph here. All right. So now we look at the inequality written in blue. As I mentioned before, this is an exponential function. This is written in the form of y equals a times b to the x. So my a value, that's my starting value, or my y-intercept is 3. But x equals 0, you're going to y value 3. And then my multiplier is 2. So every time I go over 1, I'm going to double the y value. So if I plug in a 1, that's going to be 3 times 2. I'll have a 0.1, 6. If I go over to 2, I'm going to double again, and I'm going to have 2, 12, which is way up here on that graph. Going backwards, I'm actually going to multiply everything by a half. So I'm dividing by 2, and you can see it's not going to be a perfect graph, but we get something that looks kind of like, if I can go through most of these points here, and kind of like that. All right, so this is not perfect, but we have this exponential curve. Notice I'm using a solid curve because it's less than or equal to. So we're including the boundary curve in there as well. So all the way out here. So again, we need to pick a couple of points to test. 0, 0, again, my favorite to plug in because it's easy to do. And then maybe we pick something up here like, I don't know, how about -3, 6. -3, 6, see what that gives. So 0, 0, when I plug that in, I get 0 is less than or equal to 3 times 2 to the 0. Of course, 2 to the 0 is 1. So is 0 less than or equal to 3 times 1? Yep, that's true. 0, 0 works. And then -3, 6. Let's see, we got a 6 is less than or equal to 3 times 2 to the -3. Now, 2 to the -3, remember that negative exponent, we look at the reciprocal of that 2. So it's actually like a 1/2 the third power. So this is a 1/2 to the third power, a half times a half times a half. That's going to give us a 1/8. So is 6 less than or equal to 3/8? Nope. That is false. So we're only going to shade on the side that includes 0, 0. So with this exponential function, you know, it's not a straight line boundary. It's this curve boundary line, but we're going to pick everything that's on the side that is in this case kind of to the right and below that that curve. So I'm going to pick everything over here, and that includes everything up here, anything that is on that side, but not in this upper region here. Everything kind of down here is where we're going to shade. You remember from the last video, what we really wanted were just the points that made both of these inequalities true. So where we had shaded purple and green at the same time. It's a little hard to see here, but this is kind of a boundary. And then we have this is kind of a boundary. And then this was kind of a boundary. So it's actually all of this region. That's where we had purple and green at the same time. I know it's really hard to kind of see that, but that red region is everything where any point there would make both of these inequalities a true statement. If we tried some point right here, that wouldn't work. We were shading with purple there, but we didn't shade with green. Same idea up here. That's where we shaded with purple, but we didn't shade with green. I didn't do a good job of actually shading in here, but this stuff in here was also shaded with green, but again, that was not shaded with purple. So that's some green stuff, but not purple. Here's purple stuff, but not green. We wanted things that were both purple and green at the same time, okay? So it was a little confusing. You know, it gets pretty messy. We got a lot of different colors going on here. Let's look at one more example. Once again, I've got an exponential function for you and a linear function. The first one in black is an exponential function. Y is greater than 2 to the x. So our y-intercept, that's an a times b to the x. The a value is just 1. And our multiplier, again, is 2. We're going to have 1, 2, 2, 4, 3, 8. And then we kind of go backwards. Notice this exponential function is strictly greater than, not greater than or equal to. So I'm going to have to somehow kind of graph this curve with a dotted curve. So I know it's kind of weird to draw it with a dotted curve, but you just do your best to see if you can represent that with a dotted curve. Now I need to pick some points to test out. I'm going to try 0, 0. And I don't know, the point 0, 3, looks like that might be easy to try. There's 0, 3 right there. So when I plug in 0, 0, I get 0 is greater than 2 to the 0. And 2 to the 0 is 1. Is 0 greater than 1? Nope, that's false. All right, let's try 0, 3. So I put 3 in for y. Is that greater than 2 to the 0? And is 3 greater than 1? Sure is. That's true. So we want to shade on the side that includes 0, 3, not 0, 0. So here it is. Here's 0, 3, and we're going to shade on the side that includes 0, 3. All of that stuff kind of above that curve. All right, so now we are going to try y is less than or equal to 2x plus 2. So that's just going to be a line. It has a y-intercept of 2 and a slope of 2. So up 2 over 1. I know it's kind of messy and hard to see. Up 2 over 1, up 2 over 1. And I have a less than or equal to. So I'm going to use a solid line because it has the or equal to part there. And again, 0, 0 is clearly on one side of that line or the other. And then I could try -1, 6. That looks like that's right up here. Sorry, you can't see that. That's above that, -1, 6. When I plug 0, 0 in there, I get 0 is less than or equal to 0 plus 2. Is 0 less than or equal to 2? Sure is. It's true. If I try -1, 6. 6 is less than or equal to -2 plus 2. Is 6 less than or equal to 0? That's false. So we don't want to shade on the side that has -1, 6. We do want to shade on the side that has 0, 0. And so 0, 0 is on the right-hand side or below the line. And so we're going to shade all of this stuff right here. So now it's kind of hard to see, were there any places where we had both green stuff and purple stuff shaded in? And I know it's kind of hard to see. We had this curve that was going up here. And the answer is yeah, it's this stuff in here. It's really hard to see, but you can kind of see a little bit of green stuff in there. It's all of this. This is the region. So it's a much more limited region than anything else we had. But what this is saying is if you pick any point in here, those are the only things that will make both of these true statements. So you might have to pick some fractional points to really find them. It might be something like 1.7 comma 3.2, but if you plug in the point 1.7, that's right around here, and 3.2, that's right there. Yeah, maybe 1.7 comma 3.2, that might work for us in both of those inequalities. All right, so there's two more examples for you. Your parent guide has some great examples as well, and as always, make sure that you watch these videos and you use the videos to help you complete your homework. And if you have any questions, stop by at XBlock or send me an email.